All right, so I'd like to introduce Dr. Sagi Ben-Ami from the Weizmann Institute. Sagi did his PhD, I don't remember when, but under Avishai Galyam. We met each other when Sagi was a PhD student. We worked together at Caltech on SED machine many years ago. Since then, Sagi went off to a postdoc at Harvard, where he worked, Harvard CFA, where he worked on a variety of very clever instruments, and then onto a faculty position at Weizmann, where Sagi has been doing a bunch of very clever instrumentation, which I'll be talking about today. And then in addition, was one of the people behind getting Weizmann behind the Giant Magellan Telescope, which is great. Sagi and I are hopefully kicking off a collaboration, which I hope grows broadly between Weizmann and Carnegie. So with that, I'd like to turn it over to Sagi. Thank you.
Okay. Thank you, and thanks for having me. It's always nice to visit Pasadena, and especially Carnegie. And I'm going today to talk about some of our instrumentation projects that we have been building in the past 4 years now. Two of them are ground-based arrays that are in Israel, and one of them is the first space-borne telescope designed, built, assembled, and led by Israel with the Weizmann Institute as a lead role. So let's start. As I said, I'm going to talk about the Large Array Survey Telescope, which is an imaging array. I'm then going to switch into the Multi-Aperture Spectroscopic Telescope, which is our attempt to take the last approach where we are using many small telescopes into the spectroscopic domains. And finally, I will speak about ULTRASAT. Three of my main collaborators that I'm not going to mention specifically in every slide is Professor Ran Ofek, which we work basically on almost all projects. David Polishuk is our observatory manager, the Weizmann Observatory Manager, and then Mal Kun is a staff scientist in our research group that started recently. He's a White Dwarfs expert, so everything that I mentioned, White Dwarfs is probably coming from her. And our main goal is to develop instruments for wide field surveys, from detection to classification, follow-up, and actually offer the complete capabilities. Just some historical notion or some background. Our institute is mainly focusing on transient astronomy, and we are going to mention a lot. So discovery space in astrophysics, a significant amount of the data collected today in astronomy is actually coming from surveys, and these surveys are characterized by wavelengths, timescales, luminosity, and rate. And of course, we would like to try and have them spread across the globe as uniformly and as wide as possible in order to be able to detect and follow up as many objects as we can. In terms of the timescale, we can talk about timescales of less than a second. For example, when we are trying to look occultations of KBO objects, where the timescale of the occultation itself is less than a second. We can talk about fast transients in the local universe, which have a timescale of roughly a day in the not so local universe, and of course supernova and other explosive events with timescales of weeks to years. And we already have many sky surveys going around. Some of them are also being led by people in this room. We have the Zwicky Transient Facility from just across the road, Pan Stars, SDSS-5, of course, from here, Atlas. If you're not familiar with that, that's Black Gem that is now in Russia and led by Paul Krut. And of course, we have in the future the LSST, which is going to be wide, fast beat, and so on. And when we said that, okay, we want to have the same approach of wide field of view surveys, then our main question was, how can we actually make it better in terms of the cost effectiveness? We are a relatively small university, a small institute, and a small community in Israel. And if we want to have something that we can control and we can dedicate the cadence and the science objectives, it needs to be something that single institute can actually lead and operate and work. And for that, we developed the GRASP equation, which is a metric of the volume of space that a telescope can probe per unit time. And basically, it means the proportional to rate of events or sources that I can detect with a given telescope system. So it will be proportional to the field of view, to the signal to noise of a specific standard candle that I'm observing, the amount of background and the SIG. I'm not going to discuss specifically about the powers of each term. And of course, the exposure time over the sum of the exposure and dead time, the readout time for a detector itself. We wrote a paper on that. It was published 4 years ago. And then when we are actually taking this equation and fold in the cost of a specific, or the proportion of the cost of a telescope to aperture, when we took it, for example, from Van Belle et al. In 2004, you are finding the conclusion that multiple telescopes are more cost effective than a single large telescope in terms of the amount of standard candles I can observe per unit time and per unit of money per investment. And one of the caveats here is that we need to take into advantage, we need to make sure that still our telescopes are not diffraction limited, but are plane limited. And for that, we need to be roughly at a diameter of more than 20 centimeters, just to make sure that we are governed by the SIG and not by our diffraction limit of the optics. And we need to make sure that we are sampling the SIG. This is something very important and something that until recently wasn't that possible. So there are other small telescope arrays exist already and operating for many years, similar to our own. But if we want a wide field of view survey, that means that we have a short focal length. And if we want to sample the SIG, that means that we need to have very, very small peaks. How small? We are talking about roughly 4 microns. Yes?
It's about where
They told me to give the, okay, I can just.
yeah, where side characteristics come into, kind of like the seeing the kind of the sky.
So it's the SIG in the background, which is the sky background and the typical SIG in the side. Of course, you also need to fold in how many clear nights you have per year, for example, which is not reflected in this equation. That's something that you have to consider as well. Next slide. Sorry about that. Okay. So as I said, that entails that we need to have very, very small pixels of the order of 4 microns or so. And until recently, those were not really available at large quantities and at reasonable cost. But this roughly changed in the last 5 years or so. And today you can get high quality, large format, backside illuminated CMOS detectors with very small pixels. They are off the shelf. The price is roughly between $3,000 to $6,000 per unit, which makes them very, very feasible. You want to make sure that the cameras don't cost 10 times the telescope, for example. They can be easily tested, simplified infrastructure with internal cooling to a level of roughly -15, -20 degrees. And you have multiple, not telescope, but multiple vendors that are available from. So you are not trapped with a specific vendor in case something goes wrong with that specific one. Specifically, one of the chips that today is more commonly used is the IMX455 from Sony. It is available from at least 4 companies that I found, ZWO, QHY, EMEA, ATIC, and I guess there are several more. Yeah.
Do those devices have the desired sensitivity and dynamic range?
So those are 16-bit sensors. So they do have the dynamic range. And in terms of sensitivity, you can see here, for example, specifically for the one that we are using, the QHY 600M, which gets to a quantum efficiency of roughly 0.9, a fraction of 0.9, so 90% almost. One caveat that they do have, they are still not as uniform as standard CCD, as science-grade CCDs, but they are getting there. They are not as bad as CMOSs that we have seen from 15 or 20 years ago. And for a camera that has 60 megapixels, then okay, it's natural that some of them are not as uniform, but they are definitely improved. The size of this chip is 35 by 24 millimeters, and the pixel size is 3.76 microns. So those are really, really small pixels, and when we're actually coupling them to the telescopes that we are having, which is the Celestron RASA 11-inch, you are getting to a pixel scale of roughly 1 arc second or 1.2 arc second. And then you really start to sample the thing, or being close to the thing at least, and you're starting to be less background dominated and way more efficient. So this is the array that we started to operate. We call it LAST, which is the Large Array Survey Telescope. It started as a joke because then we can say that we have the last White Dwarfs meeting or the last, and it kind of stuck. We were planning at the beginning 48 telescopes, each one with 28 centimeters. Those are f2.2, so those are really, really fast telescopes. The door limit of the telescope is 0.4 arc seconds, so this is what the optics offers. And each telescope now is equipped with a backside illuminated CMOS. We are using QHY. Honestly, they're almost identical, the QHYs, the WO, and so on and so forth. We are getting 1.2 arc seconds per pixel, so we're not sampling the thing, but we are close to the thing. And an area per telescope of 7.4 degrees. We are now moving to a new rolling roof structure where we will actually have 72, which is the maximum that our structure can hold. Right now we're on a structure that can hold only 48. Those telescopes are mounted 4 per mount. Okay, these mounted are from Xerxes, which is basically a really clever guy that builds his mounts in his garage. We bought from him one mount and then got a license to manufacture those mounts ourselves. And you can operate them either by having all telescopes pointing and parallel to each other, so pointing at the same field of view, or to adjacent field of view. In the first mode, which we call the narrow mode, we have basically a 1.9 meter telescope with a field of view of 7.4 square degrees. We are not very often operating in that mode. The mode that we are mainly operating is the 28 centimeter telescope, each one pointing to an adjacent field, and we are getting a footprint on the sky of 355 square degrees. Yeah.
If smaller pixels were available, would it be preferable to better sample the scene, or is there diminishing returns?
So you were asking if there were even smaller pixels, would it be more viable? I think we are kind of in the limit where actually the amount of noise that you're getting from readout noise and background at the faint end will actually diminish your return. The main reason here to actually go to such small pixels is mainly to take advantage of the spatial resolution and not necessarily to sample the same. So we are really close to the limit. You might want to be a little bit smaller, but it's not a very big game.
So what is the scene? You're
Okay, to that. What is the scene? So this is the site. When we started to think about where do we want to have it, we were looking at locations in Israel. Israel is a small and very troubled country these days. And we were looking for a place that where relatively the sky background will be low, and that it will be easy enough to actually for us to be on sky on a short term. We looked for several places actually in this area, but we had some problem with the infrastructure, and it looked like it's going to be 5 to 6 years until we actually be able to get a power line in this area. So the way that we actually ended up, we ran another friend that lives in a kibbutz in the south. A kibbutz is like a common community where they actually share everything from food, houses, and so on. And this is a kibbutz that's called Notzmada. It's roughly 90 kilometers south of the city of Eilat. It's in the middle of the desert. This is a real desert, very dry, roughly 2 to 3 days of rain, I guess, per year. And this is the area where we are at. It's at the outskirts of the kibbutz. We have great collaboration with them. The guy that actually runs the kibbutz for some reason have a master's degree in astronomy, so he saw it as like his own, saw it as an advantage for them. And when we're actually looking at the thing, then we sampled the thing over 2 years now already, and we are talking about median thing of roughly 1.4 arc second, which is true, it's not amazing, but given the fact that our pixel scale is 1.2 arc second is really, really nice. Okay, it's kind of fits well where we want to be. Sky brightness is the order of 20.9 magnitude per arc seconds. Not perfect, but honestly, in Israel, you cannot really do much better than that. In terms of our footprint on the sky, so we are roughly in the middle of the Asiatic gap. So this is a very good strategic point for us. There are a couple of hours that we are almost the only survey that can actually observe at a high air mass. And the number of clear nights that we have per year is more than 300. And this is a very big issue. So we are really the vast majority of the night, the sky are really, really clear, and we have no problem with operation. If I'm comparing the grasp of our system with respect to other facilities currently going, so last is here. Okay, we are roughly 4 times better than ZTF, for example. I know Atlas already has more nodes, so it's probably up there somewhere. We are, of course, not as good at LSST or ULTRASAT, which I'm going to talk at the end of my talk. But given the overall investment in this project, which was of the order of $2 million, including everything, I think this is coming out to be very, very nice and very, very efficient. And yeah.
So like normally you think of operations as about 10% of the initial costs.
Yeah.
Do you have a sense of?
So,
how operations
so you're asking about the operational cost relative to the overall.
Yeah.
I would say that in that case, it's significantly more than 10%. I would estimate it actually at 30%. The hardware is relatively low. The cost of a single laser telescope is of the order of $3,000 to $4,000. A camera is of the same order. The mounts themselves, and we have 4 telescopes per mount to manufacture them, was of the order of 10 to 12. Okay.
I mean, you have people who work there.
Yes.
That you're paying their salaries.
Yes.
And that I think, I'm guessing that's the dominant cost.
So the dominant cost is not specifically the people that are there, but the software experts and the engineers
Yeah.
that are working on that.
Okay.
And that's the dominant cost. That's like 30%, I would say, of the overall cost.
Okay.
Okay, our 5 sigma limiting magnitude in 20-second exposure is 19.6. Of course, it depends on actually on the color of the target, but it's roughly 19.6. And in a quad of 20 images, type of it's 400 seconds, our limiting magnitude is of the order of 21 magnitude. We are operating with no filter, completely white. Our relative photometry is roughly 1 millimag at the bright end in 400 seconds or so, and you can see kind of flat line here. So a little bit more than 1 millimag, the order of 2 millimag. And this is a work that we are still operating and trying to get better and better with. One of the big challenges here, and this is also one of the costs, is the amount of data. We are working at 20-second cadence exposures, 48 telescopes, and with that rate, we are talking about 3.3 gigabit per second of raw data. This is 2.5 times LSST or 22 times ZTF, and that means that we cannot really transfer all data into an observatory. After reduction, we get 15 gigabytes per second after data reduction and with the processed images and so on. So the solution is either use existing software that will require more than 20,000 cores, which is really not an option. We went with the second solution, which is to rewrite an efficient software that do data reduction online, saving raw images and process only for 1 day, doing processes on the images, looking for transient, looking for changes and so on in real time, and then erasing the data and only passing catalogs into our servers at Weizmann. This was the main work of Ran Rothbeck. My colleague is already talented person working on this effort. We are still working in order to actually improve the speed and improve the capabilities of our data reduction pipeline. Our observing strategy, which I have to be honest, it's kind of a recommendation. We kind of do whatever we want, which is the whole point of having such an observatory, is roughly 8 telescopes visiting in a high cadence, not 8 telescopes, 8 mounts, doing high cadence survey with 8 visits per night in 2000 square degrees, and low cadence survey with the rest of the 4 mounts with 2 to 3 visits per night. We have TOO mode that respond to gravitational wave, GRBs, other triggers, and so on. And we have very high cadence, which we will talk in a second. We are already fully operational, and I put here the asterisk because right now we are actually not operational at all because we are building a new structure. So current structure is sealed, the telescopes are covered, and we are expecting to move to the new structure roughly in November. One of the nice things that we did already like a month after we came online, there was the DART satellite that crashed into an asteroid in an attempt to change its orbit a little bit. It happened exactly above Israel at the time, which is one of the good reasons why you want to be covering the entire globe. And this is, for example, a movie of 4 other telescopes observing that and actually seeing the dust cloud that was emanating from this explosion. We already have a paper released on that, so that was really, really cool. And when that happened, I was actually there with the family of my wife, which were visiting us in Israel from Brazil. And while they were hanging out in the kibbutz, I was observing, so I even had an excuse why I won't continue because I don't want to get in trouble when this is recorded. So, one of the science cases that I'm very excited about, and this is my student that is working hard on that, is to find exoplanets orbiting white dwarfs. And the idea is you have a white, you don't need to explain to you guys what is a white dwarf, but if we are looking for remnant planets in short orbit around white dwarfs, then we are expecting very deep occultation, but we are also expecting them to be very short. And with the current surveys that we're looking for that, we know of one very clear short orbit planet around white dwarf. This is WD1856. It was discovered, I think, 4 years ago in space data. It's a very bright white dwarf. And you can see here how the light curve as it was taken with LAST, the big advantage of LAST that within the limited magnitude that we can have, we are talking about roughly 40,000 white dwarfs that we can actually scan in a relatively short period of a year or 2 years, standing on each field for 2 to 3 nights in a row. And then if we don't find anything with a short period, then we can actually move to the next field. We kind of vetted this field, found whatever we found, and we can move to the next one. And this is one of the efforts that we started right now. This is one of the projects that are really cool for us because we can do with the telescope, as I said, what we want. So we have four months roughly that are just looking at the same field for 8 hours every night, 3 nights. They finish that, they move to the adjacent field that is in high Hermes, and repeatedly, so on and so forth. We already have several nice candidates, not planets, admittedly, but nice phenomena. And of course, the most interesting thing is what you find that you didn't expect to find. Okay, I will move to our next array. So this is an imaging array. And the main issue here is that, okay, imaging is relatively cheap, right? You need to have a telescope and a camera. And you get many targets and many viable candidates. The problem is that when you actually want to go and see, okay, is this actually an interesting target, or did I just saw some kind of writing that doesn't really have an interesting phenomena behind it? You actually need to go into spectroscopy. And as you probably already know here, problem is that we have way more candidates detected than we actually have spectroscopic time. Spectroscopy is a photon-hungry observing mode, and of course you need to have a large and efficient telescope, and you can typically do a limited number of targets specifically if they are spread over a large field of view. Also with the missions like Gaia that release a lot of interesting data sets, we want to really have the capability to monitor and study those data sets in spectroscopic modes. And our question was, okay, how can we adopt the last approach, the Large SRB telescope approach, of using many telescopes, cheap telescopes, available telescopes, and make it and adopt it into the spectroscopic domain. And our answer was the Multi-Aperture Spectroscopic Telescope, which stands for MAST. So as you can understand, we are trying to follow the same naming convention. This is my colleague, Ofer Yaron, who is managing the project with me or for me. And the idea is to take an array of 20 telescopes, each one 24-inch, very simple telescopes. When you combine them together, you actually get the collecting power of a 2.7-meter telescope, and then combine the light from all of them together with an array of optical fibers and feed them to specific spectrographs that are located in an instrument room down the road. The big advantage here, of course, you can either operate it as a single 2.7-meter telescope, or you can actually add, because each telescope is mounted on an independent mount, to actually have each one pointing to a different direction, and have 20 telescopes, each one with 60 centimeter mirror, but observing very bright targets, for example. As you understand, I hope from this image, we are actually not trying to combine the beam coming from all the 20 telescopes. We are imaging each one independently on place on the detector, and then combine them after image processing, with the advantage that we can then do that, because the light is not necessarily combined. Of course, there is a penalty here in terms of readout noise, but I will talk with you how we actually deal with that. So what did we do? We contacted Flamewave, which I'm sure you are familiar with, and asked them to fabricate for us this telescope, which is very similar to the standard CDK series, but it's actually a single parabolic mirror that operates at f3. There's no secondary here. It's just a single parabolic mirror that operates, that offers a very fast spin. We choose specifically f3 because that guarantees minimum focal degradation when I'm going directly into a fiber without reprocessing the beam, so with no relay system. Okay, so automatically these telescopes were designed to be very simple and to offer a beam that is easy to feed into a multi-mode fiber. We signed a contract for 20 units. We already received 9 of them, and we are receiving them at a rate of roughly 2 per month. They are mounted on this equatorial mount. It's L550, also from Flamewave, and where they will be housed in 2 structures. Each one can hold 10 telescopes also. One of the things to keep in mind that because we just have a single parabolic mirror, our image axis on axis is basically perfect, okay, or almost perfect. However, our image quality deteriorates very fast because of coma, and I will show you that. I should give some credit to our software engineer, Ms. Arya Blooms, who's doing a wonderful work on actually operating and writing for us the software that controls those telescopes and make them operate simultaneously with all the subsystems that I will describe shortly. We are basically having our own software suite that sits on top of the Flamewave software, which seems to operate very well. This is, for example, image from the focal plane of our telescope. You can see that on axis, the image looks very, very nice. This is, of course, the ring nodula. However, when you are going away from the optical axis, which is roughly somewhere around here, you can see those, we call them medusas or fishes or whatever, and they all point into the center of the optical axis. This is exactly the definition of coma, right? The images are very, very much coma controlled. But how can we actually make sure that the fibers at the end of the day, the beam is actually fed into a fiber and that we are guiding correctly on the fiber? So the idea is as follows. We developed these units, this fiber coupling unit, where the beam on axis is actually hitting this fold mirror that you see here and is directed into the optical fiber that is connected with a standard FC connector on the side here. However, the surrounding field of view that is not blocked by this central obscuration is imaged on a detector that is found here, and we make sure that those two are actually confocal. And we have a special setup using distance indicators, laser distance indicators that can guarantee that the distance from here to here and here to here is equal to a level of 5 to 10 microns or so. That's guarantee the confocality of the focal plane here and the fiber face here. Now, this is how it looks, by the way, when it is assembled. You can see here, this is the fold mirror, and you can actually see, so this is the fold mirror, and you can see here the two fiber connectors on the side. One of them is for the science, the other one is for sky. Okay, and then the rest of the field of view is actually hitting here, where this is the focal plane that you can see here. Okay, attached here. This is all, by the way, mounted on the telescope focus. Okay, and is also have an interface with the linear stage that I can move this in and out, this entire thing as a single body, just to examine, for example, the beam quality on axis and make sure that I can control the focus, because it's very hard to focus those telescopes because of the high coma if I'm actually not observing on axis the image itself. The way that we are actually doing tracking and guiding, we are solving the image, the surrounding image with the central obscuration every time. Okay, we are using a PlaneWave software with our own suit on it, as I said. And this is, for example, the tracking error that we accumulated. You can see over time. And this is what we get, for example, after correcting with the mount, solving on each image repeatedly. And so far, we still didn't have a case where we couldn't really solve the field. So this is really operating very well with shifts of less than a pixel or so. Okay, and we are very happy with the performance of this unit. The fibers we are using are
Wait.
Yeah.
So, how do you know the star is on the fiber?
so basically in most of the cases I cannot see the star, right? Because typically what I will try to do, I will try to observe an 18 magnitude. I will try to take the spectra of an 18 magnitude supernova, right, which I cannot really observe in a short exposure. So we do have finding charts, accurate finding charts that we can trust in advance. We are solving the field before.
So you're relying on having good coordinates and
Exactly.
using offset guide stars.
Exactly. Yes.
Then you make a full solution. Then
Yes.
the other question is, how do you determine the position of the fiber relative to the offset?
Okay, that's a great question. So a couple of things which I actually omitted because I didn't want to be too technical from that. First of all, we have a special jig that I can actually plug in our system and then calculate, not calculate, but actually directly measure what is the corresponding pixel on this camera that is registered with respect to my science fiber. And we can do that, and we prove that we can do that to an accuracy of 5 microns. Okay, so we do that. Now, the detector here and our fiber are a single unit. There's no flexure between them. Okay, it's a single unit of aluminum. So I can correct for that. We don't only rely on that, we actually put something on the other side that honestly to these days we didn't really use, but we have here another option to put in a fiber. This mirror is actually double-sided. And the fiber coming from here that is focused on my detector is actually hitting the back of the mirror and is directed onto my detector. This fiber, we register it in the lab. There are those screws here that you can actually move the target. We register it with respect to the fiber here, and I can always turn on my light source here and check which fiber, which pixel is actually registered with respect to my fiber here. Honestly, to this day, we already had several nights working on admittedly a single unit testing it. We didn't find any reason to test it, but we are still allowing that to be there in case that we find out more problems in registering than we actually think.
What's the diameter of the fiber in seconds?
So right now, okay, Okay, so right now we are basing either 25 micron or 30 micron fibers. We are still haven't concluded which one. We're actually purchasing two fiber ones. 25 arc second on the sky is roughly 2.6 arc second, 30 micron is roughly 3 arc seconds on the sky. We want to go with multi-mode fibers. We don't want to go to a single mode fiber just because of the efficiency of coupling. Okay, and this is measurements in our fiber testing unit that we find out that with relative to a complete F2 feed, we have roughly less than 7% FRD. Okay, this was verified also with at the University of Chicago. We sent them some fibers. The guys that worked on our own asked them to measure them as well, and they confirmed our results. Right now, we are manufacturing two fibers, and I said 25 microns and 35 microns and 30 microns, and we will determine which one to use as we gain more experience with the telescopes themselves. So we do have like a 1 arc second margin with respect to guiding errors, and I hope that it will be enough. Okay, in terms of the spectrographs that we are designing for them, so we tried to have like two different sides of the same, two different sides of the balance between SNR and resolution. One of them we call it deep spec, which is a low resolution prism-based spectrograph with a resolution of 500. And the other one is high spec, which is a high resolution, a relatively high resolution of the order of 20,000, but very narrow bandpass. So it's dedicated to actually look at specific lines. And we have three gratings. Those are ion-dash gratings, calcium 2H and K, magnesium 1BH and alpha. Because of the narrow bandpass, this is mainly for galactic sources, while this is more of a general purpose spectrograph. Deep spec, the idea is that we are splitting the beam to 4 different band passes using these very efficient decoys, and then we are dispersing each beam with a standard prism. Each prism is actually made with a different apex angle and different material, and so we can actually each one of them balance the resolution curve, not to be flat, but actually to give an average of 500 or so, a little bit more, and this is all calculated with the 30 micron fiber, by the way. So we can get like a resolution of 500 so, resolution of 500 or so, and on the other hand, be very, very efficient because the losses that we have on the prism itself is just the area coating losses, while the lenses of each of those bandpass is just a doublet, and just a doublet that can also be designed very, very efficiently. Each of these arms has its own detector. It's a 1K by 1K detector, standard B2B detector. And in terms of the SNR, you can see here what we expect to get with the properties at nodes nadar, for example, for a single trace. This is roughly 300 second exposure. And I do believe that this is a little bit optimistic, but we still think that it relatively places what we are expecting to get. We are expecting to get, for example, with 17 telescopes, 17 traces, roughly 19.5 magnitude. Science cases for here, of course, classifying transient events with a resolution of 500, it's more than enough to actually tell me if I'm looking at a type 1A, type 1C, or type 2 core collapse supernovae. And one of the things that our department is really focusing on today is trying to find a core collapse supernovae immediately after explosion, for example, with glass. And there is signatures that there is CSM signature when you are going and taking the spectrum very fast, very rapidly after the explosion. You can see remnants from whatever the environment in which the explosion occurred immediately after. This is the work of Abishai Galyan and his team. You can see this now flash features that actually disappear in 3 to 5 days after explosion. So if you don't take a very rapid spectrum, you will not be able to see them again. And of course, they give you a lot of information about the environment and what happened to the exploding star immediately before the explosion itself. This is always also why it was important for us to try and push the resolution as high as possible. We went to a resolution of 500 because it's enough to actually detect this relatively, okay, it's relatively now feature for such a fast evolving phenomenon. The second instrument, as I said, we call it iSpec, and the idea here is actually to use ion edge gratings. We already use them in a different spectrograph that we are now commissioning. And the idea is that you have basically two parameters, the depth of this binary mask and the width, and you can get actually very, very high efficiency, but over a relatively narrow bandpass. So you can scratch them with very, very high density, the density of the grooves. But within this bandpass, you can get a resolution of more than 90%. And this we already measured in the lab, and get a resolution of 20,000 or so. So this really puts us in the same field as much bigger telescopes when they are using the Recherche spectrographs, for example, to look at such events with a relatively small array. As I said, we are using 3 gratings at the moment, but we have a cassette here that can plug more and more gratings as we want. We are just moving the required grating into space, into the right position. We have the calcium H and K, magnesium 1B, and H alpha. We already got 2 of them from Fraunhofer in Germany, and we are now going to get the third one in 2 months or so. Yes.
I was just gonna ask who's making the gradings.
Okay, so who's making the gratings? Fraunhofer in Germany. We found them to be the best ones in delivering those. This is my student. She's working on this project here, Sophia. She's doing a great job. The design is very simplistic. The fibers are standing here, as you can see, and we have a Schmidt collimator with 100 millimeter beam. These gratings are roughly 45 degrees, a camera, and our detector. One of the things that you probably want to ask, okay, but you have 20 traces, especially for high resolution, that's a problem. So what we are doing here, we are basically using EMCCD, where we have amplification before the readout, and therefore the penalty that we get from the readout is relatively small. So this is how we try to mitigate the penalty of the readout. In case of the previous spectrum, because of the lower resolution, it's not a big deal, but when you are going to our resolution, it does play a factor. It does play a factor, and you can see here, for example, our comparison between if we use the regular CCD and EMCCD, or if we were at the Poisson limit. And again, this is our estimate of what is the SNR that we are going to get as a function of magnitude. Okay, yes.
I think you picked this before QCMOS was on the market, but have you looked into the QCMOS?
No, I did not, but it's true that I picked it before, so.
Yeah.
We have the detector now for already 3 years, so there might be better options. One of the downside of those MCCDs is that they are basically very, very expensive. And they are also available in relatively small formats. This is another downside. Okay, main science cases that we are looking for those specific 3 gratings. So UV radiation, radiative environment of White Dwarfs. We know, I will talk later about compatibility, so I wouldn't focus on that now, but calcium H and K line are an indicator of FUV emission because they are exactly at roughly the same temperatures. Given the fact that FUV is very hard to measure for stars, we can monitor the equivalent width of the calcium H and K line. Okay, and then determine habitability. This is a work that we already start doing for using other methods, but this is one of the things that will complement ULTRASAT capability, which we will talk about shortly. The other thing, as I said, we are trying to focus now on White Dwarfs. And for example, if you want to measure radial velocity of White Dwarfs, also basically based on the core of the age alpha line, okay, measuring the width of the core of the age alpha line. And with such an efficient spectrograph coupled to an array that we basically own, you can really have a wide survey of roughly 5,000 objects determining the radial velocity, looking for white dwarf binaries, and so on. Okay, the last one, the magnesium 1B and the calcium H and K together, if we are looking, for example, at polluted white dwarfs, then the ratio of the calcium pollution in the white dwarf atmosphere to the magnesium pollution can actually tell you a little bit about the material that that the white dwarf was accreting, and using that you can tell a little bit about the history of the planetary system around the white dwarf. So this is another reason for us to choose those specific ratings. And as I said, we can just put in more ratings as we find more science cases to plug in. How does that all sits together? So this is our array looking from above. The fibers are around here. Okay, this is the output. They are illuminating to this side. Okay, in a linear array. And we can basically move this stage from illuminating this collimator, which is what we call deep spec, or illuminating the bottom. And then you get this Schmidt collimator and high spec. Okay. This is, for example, our fiber linear array. It's manufactured by Fiber Optic. I will give you a second now. We can actually have two companies manufactured, and then pick the one that is better. So them and Fiber guy, and you can see here how actually this is all supposed to operate. The precision of this stage is between 1.5 and 2 microns. This is made of this is able precision stage, and this is more than enough to actually position the fiber output in each of those collimators, and then you can also switch between the two instruments very rapidly. This is how it looks when it is all assembled in the lab. This is our prototype fiber unit, and we are now starting to mount all the optics into the mechanics. The last mission, any questions, by the way? Take the opportunity to actually sip some water. The last mission or the last project I would like to present is ULTRASAT. ULTRASAT is the first Israel-led space-borne telescope. There was actually one that was already built but never saw space. But this is the one that we hope will actually be launched into space. We are certain it is. It's a wide field of view near UV space telescope with real-time data load of 15 minutes or so. High cadence observations. Continuous field of view, so it basically ogles into a specific field most of the time, with target of opportunity capabilities of 50% of the celestial sphere at any given moment. You can see here the list of people, or what we call the program office, that is involved in this project. The funding partners is the Israeli Space Agency, the vast majority. Third comes from actually Weizmann internal money. NASA is giving us the launch. We signed an agreement that in return for 10 PIs joining the science team of ULTRASAT, we are getting a launch into orbit, into GTO orbit. And DESI is our German partners. They are assembling the focal plane array. The industry partners are all from Israel. IAI is the Israel aerospace industry. LOP is our OTA team, OTA company, and Tower. Just semiconductors are manufacturing the detectors themselves. This is spacecraft when it's assembled. Our telescope is based on a Schmidt design, and we'll talk about it shortly. It offers a field of view of almost 200 square degrees, okay, with a spatial resolution of 7 to 10 arcseconds. And our camera is based on four 45 millimeter dies. Mounted together in a continuous mosaic, as you can see here. The PI is Eli Weizmann, Professor Eli Weizmann from the Institute, and Yossi Schwarzwald is our project scientist. The science case, of course, gravitational wave source. We have a gravitational wave detection. We already know that we expect to have prompt electromagnetic emission in the UV. And with the error expected from the next generation of GW detectors at 200 square degrees, enough to actually engulf the full error area of any detection and try to detect this event as fast as possible. Of course, core collapse supernova, trying to find events as they happen, because the prompt emission, the shock breakup, happens in the UV. Target disruption effect events, M flares, asteroid, and many other. One of the leading science cases, as I said, supernovae explosion, specifically core collapse. You know, there are several types of supernovae, specifically overlap supernovae, from type 2P, which is like the standard hydrogen rich exploding giant star with a large with a long plateau. We have the type 2N, which shows some signs for interaction not only 4 to 5 days after, but for much longer period. And then, of course, the split envelope overlap supernovae. But we don't know exactly which star goes explode in which supernovae. And if we actually detect them fast enough, of course, we can actually try to look for detections before the explosion itself, as happens here in one case that was published 15 years ago. I think that there's one or two more cases where there was actually detection of the star immediately after, which the star was able to detect it in data before the explosion, but not that many. Another alternative is actually to have early, meaning less than 1 day, UV emission that carries unique signature with the shock breakout as you detect it. It can tell you about the progenitor size, the explosion prototype, and the pre-explosion evolution. I think there are experts from that.
Yeah, I may have missed this, but what's the wavelength range of the instrument?
220 to 290 nanometers. Okay, so it's near you. It's roughly equivalent to the galaxy. And we expect to have of the order of hundreds of detections after 3 years, and that's based on synthesis of detections in the transit name server over the past, I think, 10 years or so. Another interesting science case is habitability around M dwarfs. You know, those targets are very active in the UV, and of course, if they are looking at nearby stars, then UV emission can make those planets uninhabitable. However, we don't know a lot about the UV environment around those stars, and part of it because they are very active and you need to actually monitor them over extended period. So, given the fact that this large field of view, we allow tens of thousands of M dwarfs within its field of view at any given time, we are monitoring them continuously, we will be able also to detect and determine the frequency of the more rare but much higher energy flares that can really make planet uninhabitable. We already did some work trying to understand what is the frequency, what are the frequency limits at the moment, and what we expect to get from ULTRASAT, and this is actually been published last year by my student. The focal plane array, as I said, it's based on tower detectors, 9.5 microns per pixel, 5.4 oxygen on sky. Each single tile is 7 by 7 square degrees, and we have 4 tiles. Reader time is below 20 seconds. Reader nodes below 3.5 electrons. You can see the rest of the parameters here. This is all been published in several SPIE papers. The dies themselves have already been manufactured, and they are now being packaged by STA. And I don't have Greg from STA used to work here in the device, right? So this is activity going on right now. Another interesting stuff that we are doing now is we started a campaign with ACTAR, which is the black expert coater guys, to actually coat this rim around the detectors to reduce back reflection from the detector. So this is also going on, and very interesting to work with them. The quantum efficiency of those detectors you can see here. This is the one that we actually chose, the solution that we actually chose. This is measured, not simulated. So we have a peak efficiency of the order of 80%, and we have the dies already manufactured. The telescope itself, this is a modified Schmidt design with 2 large spheric correctors and meniscus correctors. One of them, the external one, is made from fused silica, and the internal one from calcium fluoride, which is almost the only place you can work in this wavelength. We have 2 fit flatteners and a spherical mirror on the back. The aperture itself is 33 centimeters. Okay. One of the challenges, many of the elements are already manufactured. This is the Schmidt calcium corrector 33 centimeters of $1 million optic. So it's very nerving and eye-nerving to actually hold this in your hand. We have there the field flattener, the mirror as it is being polished, and the bezel of the telescope. And this is the focus mechanism. We actually control the focus by moving the field flattener to in and out. And, one of the challenges that we have is how do we actually suppress light at longer wavelengths? So we use basically two filters. One of them is a sapphire filter that is located just in front of the detector, 500 micron out front of the detector, that offers 2 orders of magnitude attenuation between the visible and the UV. And you can see it here. It was developed in collaboration with VLV, and we already have the NFM delivered. And the other unit is a black mirror. So our spherical mirror is basically reflective in the UV, but transmissive in the visible. Okay, the back is coated with that to absorb the visible band radiation, and it offers also roughly 2 orders of magnitude attenuation. And when you combine those two together, you get the 4 to 5 orders of degree attenuation that you want in such a telescope. Another challenge, such as wide field of view, is stray light. So we designed this very unique bezel with changing orientation of the fins as you go out. Basically, I always make fun that it's a very big buffer and a small telescope connected to it. Another role of this buffer is to protect or reduce chance of radiation in the external lens. So as high energy electrons transmit through the Schmidt corrector, they actually create UV radiation because of chance of radiation. The speed of the travel speed of the electrons in the material itself. And those are actually contribute to the background in our detector, because the filter, of course, doesn't block them. They are in the UV, but with this large buffer and the fact that we're actually thinning the outer edge of this buffer, not thinning, sorry, making it thicker, we actually reduce the amount of high energy electrons that actually reach the external lens. This is the total throughput that we expect of our system, and this is actually already based on as-built data, so this is not theoretical by any means. This is the expected PSF performance, because it has dependency on wavelengths and on position on the detector. And because of that, we're actually going to have different limiting magnitude for depending on the SCD of the target, and this needs to be taken into account. You can see it here, for example, the limiting magnitude for an M dwarf with that will result in a larger PSF because of the relic that is not avoidable. And comparison for that for a black body of 20,000 degrees and a G dwarf. And this is our estimate of the overall background noise, making sure that it is not dominated by triangle or zodiac, which all stray light, and this is all what the buffer is basically doing. This is the system itself when it is assembled on the telescope itself. This is IAI, it's aerospace industry. And this is how it looks. This is actually the structure of the effort. Now is being delivered to IAI, and we will start integration soon. We are expecting to be launched in the last quarter of 27, first quarter of 28. And that's about it. Thank you.
Okay, great. We have time for a quick question or two.
There was a slide where you showed the number of expected sources, ULTRASAT and ZDF and LSST, and I think it was maybe for red supergiants, RSGs, it was much higher for ULTRASAT. So I was wondering, yeah, why, where that's coming from? Yeah, this one.
So in general, we are expecting red supergiants will go as type 2P supernova, right? We are expecting those to be more numerous in the sky, right? We are detecting more type 2P supernova than we are observing type 1P or 1C, right? So this is actually reflected based on the amount of detections that we have.
Sorry, but I'm just wondering, why is ULTRASAT so much more efficient than ZTF
Ah,
and
because,
LSD?
okay, because of, first of all, you are observing in the UV. Okay, and we are talking about young detection, so less than a couple of days. I'm talking about detecting the supernova one. Actually detecting at least short later, or short cooling. And the main reason is because we are observing in the UV, and because we are observing the same field simultaneously. So we are basically having 200 square degrees, and we are just looking for new explosion within this field of view. So our chance of actually detecting this as it happens, it's much higher than, for example, ZTF or LST that first of all observed in the visible. So they are already at least a day lagging behind us until the emission in the visible becomes detectable. And the cadence itself, because we are continuously observing and they are going into the same field roughly once or twice a night, depending on the specific.
Okay, great. Let's thank Sagi.